and welcome also from my side. And yeah, thanks for joining, having the patience and taking the time. So that session is called High Performance NFVI and Aspects of Multi-Dimensional Scaling. So let's have a look on the agenda, what I mean with that. So there are multiple trends fueling each other. So an example, 5G, edge cloud, containerization, disaggregation, they all play together to some extent. Then we see impacts on data center architectures. Actually, I just picked one topic here, which is about east-west traffic, very brief part of the session. Then putting some focus on telco cloud efficiency, being aware of server architecture, potential bottlenecks, things what we need to keep in mind. Having a brief look on smart mix, if they can help to increase the overall telco cloud efficiency. And then also another very brief, just a single slide to become aware of new battle in the data center or the architecture probably changing. So between AMD, Intel, ARM, x86, having a quick look on this one. So basically, what we see is actually, as I mentioned it already, we are in a large transformation process. So we go from centralized to distributed, from integrated to disaggregated, and there are multiple architectural shifts which are happening those days. So the cloud actually becomes the dominating concept, and is actually moving by itself at the same time from a centralized to a distributed architecture approach. On the mobile side, mobile standards from 5G onwards, relying on cloud-native principles. We see here also disaggregation is kicking in, former monolithic functional blocks being separated. We're having a user plane function being more positioned on the edge side in order to reduce latency, while the control functions are being better hosted on the central side. That's the same principles actually applying to mobile, to broadband. We see it, the disaggregation approach, we see it in the 5G O-RAN. So all over the place, those different trends actually fueling each other. So if we look on what is potential impacts is from former monolithic functional blocks, we are moving now to a type of microservices, micro segmentation, and previously we had either monolithic black box solutions. Also, we call them appliances, or even with already what happened already with virtualization is that even if it was already disaggregated from software to hardware, hardware got exchanged. We are relying on x86 infrastructure, but from an application perspective, the application itself was still rather monolithic. So we have seen that as a first step of somehow cloudification. It's running now on x86, but from application perspective, in the original virtualization task, it did not change too much. But now with containerization, we are going to microservices, many functional blocks being scheduled all over the place, somewhere in the data center, not necessarily on the same hardware. And of course, those different services, they are having communication with each other. They talk via the APIs, and they are actually talking quite a lot. So in a nutshell, it turns out that with the distribution of services and further segmentation into microservices, that the network becomes even more important than it has actually ever been before. So if we look now on a typical data center architecture spine leaf fabric, so that is actually defining. Yeah, well, probably maybe I should start from that one. The most discussions are very often being abstracted, and very often we just talk about the cloud, but there's still, of course, a physical network underneath, and that physical network that builds the outer performance boundaries. So unfortunately, we are not having this infinite bandwidth, what application developers very often assume, or they simply very often don't really take care about bandwidth constraints inside a data center and what are the physical infrastructure is providing. So once we plan data center IP fabric, we select the appropriate network speed depending on just what is currently on vogue at that time. It might be 1G, of course, not anymore, but 10G, 25G, or even going to a higher speed. And accordingly, we are connecting we are designing also the interconnection links. So actually, the first by purpose bottleneck is to cost savings and based on experience. So we usually have an oversubscription ratio between access links and the actual bandwidth in the fabric itself. So a ratio of 3:1 is something like usually a good starting point, a common design. Of course, it might change if you know your circumstances better. You can also probably better look on, probably less is suitable. But 3:1 is something like a typical number here. And that even is changing, is then being adjusted regardless if we are with 10G access speed or if we are going to a higher access speed, 25G, then of course also the fabric upgrade is going to happen, and then we also increase the bandwidth there. So in the past with appliances or even with virtualized applications on a server, we mostly were taking care about the north-south performance, which is indicated here. Here it is by the green arrow. That means we are looking on what is the incoming traffic from outside of the data center. Then it needs to go to an appliance or to a server, is being processed there, and then it goes either goes back or goes somewhere else to the internet. But there's mainly the focus has been on north-south traffic. But with more and more microservices are kicking in, actually the so-called east-west traffic becomes very important, and it needs to be considered. So with more and more microservices happening, the east-west traffic will also increase. So there's one important statement from Facebook. It's out there with regards to the overall bandwidth growth they had to deal with. 75% of the overall bandwidth growth was actually coming from the increase of the east-west traffic. So it is really a massive explosion on traffic inside of the data center, which basically is then being introduced or being a consequence of microservices all over the place, going away from monolithic applications. So that's one aspect of what needs to be addressed, what we need to look on, and what is probably not entirely new, but at least we need to keep an eye on it if we are designing data center architecture and if we are looking on what are the performance needs here. So let's have a look more on the application side itself. So applications can have demands for different things. So they might be memory demanding. Then we need more RAM in the servers. They might be CPU demanding. then we are looking for CPUs from Intel, from AMD, which are having more cores, maybe also looking for a server system with more sockets that we can put more CPUs in it. They might be also IOPS demanding, and then we better look for CPUs with a higher frequency. In comparison with if we would now choose a CPU from Intel, which is providing more cores, it would probably not help us that much here in that case. Of course, storage is also a factor, and then if we go more to the networking side, packets per second throughput. So that means fast packet processing is one parameter we need to look on, and then of course gigabit per second throughput, which is simply then the available bandwidth which is there. And actually there might be for sure there's actually much more. So the main thing I want to say is that applications can have very different demands, but the main benefits of a cloud, they actually come from a universal approach to host multiple applications with those different characteristics on the same infrastructure, with the same automation and operation. So basically the question is how we are dealing with that and addressing those different characteristics. So here in this slide, I'm showing two possible ways, very high level, very simple in a PowerPoint format, possible ways how to plan, optimize and make your cloud resources available to your applications. There might be either one big pool and schedule your applications in the best possible way, or provide multiple resource pools which already reflecting somehow the different application characteristics. So now in a typical cloud orchestration, we have the so-called application scheduling, which is responsible to leverage the available resources and distribute the applications accordingly. In OpenStack, in example, it's so-called Nova Scheduler. Same thing is happening with Kubernetes. So those schedulers, the standard behavior is actually to place the application in the most resource optimized way into your infrastructure. So the goal is getting as much as possible applications into the available cloud resources. So basically, the schedulers are playing some type of let's call it cloud Tetris, and is trying to squeeze as much as possible applications into the resources. So basically, with my poor PowerPoint skills, and it looks like that. We have the different building blocks, the different flavors, and the scheduler is trying to position it so that it can achieve the best result. But however, the standard scheduling is not always providing the most optimum performance. So especially if it's about application with special demands, such as low latency or high networking requirements, they are, with the standard scheduling mechanism, they are not taken care. So to deal with such requirements, we can work with so-called affinity, also anti-affinity rules, in order to force the scheduler to avoid a certain behavior, what we would see with a standard scheduling process. So, but in order to configure those settings in the right way, so we must be aware of the server architecture and potential bottlenecks and which constraints might exist. So and here basically I'm going to an example where we see a typical server infrastructure, also server architecture inside of the servers. So maybe let's start here on the right-hand side. We have potential bottleneck is coming, of course, from the network side, which network speed we are configuring. That's obvious, that's clear. Need to keep that in mind. We Also, how the network interface card, which is in the PCI bus, is basically being attached. That's happened inside of the server, but there might be a bottleneck as well. At least there's some architecture, and we need to know about it. So, and if you go to the CPU, we have here a typical server very often being used, a dual socket machine, which is hosting 2 CPUs. And first of all, of course, those CPUs, they are holding the main resources, so they're having the available cores. And if we have a dual socket system, we can put in 2 CPUs in, so that means we are having 2 times of the available cores. Here in that example, quite low, and meanwhile the numbers moved up, but the principle remains the same. But between those 2 CPUs, we have actually another thing. It's called the QPI, or the Infinity Fabric in AMD terms, which is basically connecting those 2 CPUs. And then, of course, we have also the RAM, and we have even memory lanes. Actually, there's much more, but I left that outside. So for that simple example, maybe we just have one more look on the number 5 here, which is the virtual data plane. So in today's cloud orchestration, if it's OpenStack, if it's Kubernetes, there's also a virtual data plane, which is providing networking functionalities, SDN functionalities, and so on. And basically, it's the packet forwarding. And that's also being a task which is running on the physical, on the CPUs here. And also that one comes with limitations, and we need to look on. So, and in the next one, I'm having an example. Actually, here it's called the analysis of the effect of core affinity on high throughput flows. Here you have the link, you're getting the slides, and there's actually also more to see. It's quite handy to read, and they investigated actually much more, so that's a simple example. Let me translate quickly the task. So they are setting the core affinity, so that means they are scheduling the application and also the flow handling. They're having 2 tasks. It's application processing, generating the packets, and it's the flow handling, so the packet forwarding. And they are scheduling that on those given resources. It's with those 6 cores in 2 sockets. And very important, it's multi-threading enabled. So it's basically 12 by 12. It's 144 combinations, what are being possible. So, and then they are achieving different results. The maximum throughput is 40 gigabit per second in a single flow. Quite an extreme example, but that's fine for the moment here right now. But however, what is popping up immediately into our eyes is this diagonal line. So make it maybe more visible with that one. Here on the small numbers, what we see here, I hope you can read it. Otherwise, you can use the dots. That is first the bandwidth number, which is being achieved. But we can also say as more full the blue dots are, as closer they are to the desired speed of 40 gigabit per second, and as more empty they are, then as less performance has been achieved. So what happened here on this diagonal line, it's quite logical. I said we are having 2 tasks. It's the application processing, and it's the flow handling, and they need to be scheduled. I was also saying we're using multi-threading, so that means a single core can be shared between different tasks, and then the 2 tasks are interrupting basically each other and sharing the resource of the single core. And that's exactly what happened here with this diagonal line. The 2 tasks of application processing and flow handling has happened on the same core using multi-threading, and we are ending up with quite, let me call it, poor performance. Of course, we also share the resources, but the result is accordingly. We have roughly about 20 gigabit per second throughput achieved, not the 40 what we want to have. And then if we go further, we can separate it basically in 4 quadrants. And then they are also logical to the interpretation is those on the bottom left side and the upper right side, we are achieving the full performance, so 40 or almost 40 gigabit per second. And this is always the case when the 2 tasks of application processing and flow handling being on the same socket, but not on the same core. So that means either here both tasks or those both tasks are being on socket 1, achieving then the best performance. And then that leaves us with the 2 other quadrants, which is basically then if one task, application processing or flow handling, being then scheduled on the 2 different sockets. And then they have to cross the QPI. There's probably some impact coming from the memory lanes, which DRAM is being used, and so on. And here we are seeing also some significant impact on the performance. So basically, according to this diagram, there is one setup which really should be avoided. And the other ones we need to think about how to handle them. I could say now that there is something like a business class and an economy class. So business class would be if the application is close to the flow handling, to the packet forwarding, and the other applications are getting less performance. The main point is, well, there are different mitigation strategies. That is entirely up to you, how you want to handle it. Either focus on the smallest performance possible and then being happy if you get more, or schedule your most important or those ones which are having high requirements with regards to network forwarding closer to your data plane, to your virtual data plane. Different possibilities, but the key point is we need to be aware of in order to set the affinity rules in the right way to achieve then the performance we are desiring. We want to reach. One more thing is here, so the virtual data plane, already mentioned that. That is consuming also cores on a main CPU. But another mitigation strategy could be actually to move that out and to free up additional cores here, just being focused on application processing and let the packet handling, the flow handling, let that being done and move that out to the network interface card. And that is then actually then called the SmartNIC with the data plane offload, and which would bring me to another topic on the next slide. But that is also some way of mitigating this challenge, what we see here on the server architecture. Of course, meanwhile, the servers and the CPUs from Intel, from AMD, they became much more performant. So that means a single socket system. Maybe if you are having then enough cores, if that provides enough performance to you, could be an option. So there are multiple ways. So now let's focus on moving the data plane towards the SmartNIC. So first of all, I found that analysis about network interface speed. So if you are planning a cloud infrastructure right now, a data center, for which speed you should actually go, as always, the answer is it depends. But 1G, even 10G, and for sure 40G, probably not a good choice anymore in those days. Mainly 25G. 50G looks like some niche solution still exists, but the main is between still going with 25G or looking on 100G. It's about to ramp up. Now it depends on you. What is your depreciation time? What is the need of your applications? Actually, maybe the most important thing. What is how performance hungry you are? how flexible, how agile you are deploying new architectures. Does it rather take long, maybe because of financial concerns, or is it you're exchanging your infrastructure more often? So that plays basically in your decision matrix if you go with 25G or being already leveraging on 100G, and of course the bandwidth, how bandwidth hungry your applications are. And coming back on the SmartNIC, they are not entirely new. SmartNICs since being a while on the market, but we see it here also on the adoption rate, struggling somehow to get into the market, to find its place. The hyperscalers using them since a long time, but they have a very well known, a very dedicated use case. With this diagram here, it's actually the broader market with all its variations. So it looks like now they are ramping up, they are finding their place, and basically sharing between with standard NICs and smart NICs use case, basically shared somehow. Cannot say it really, but maybe half or something in that range. There are multiple generations of smart NICs being available. One of them is, or probably those generations are not being meant in the context of one replacing another. It's more like they were appearing on the market. So ASIC-based is the longest time available on the market, very cost-efficient, but also then challenging from programmability, and especially with new use cases where the ASIC has not been designed for. That doesn't work, of course. So FPGA-based is now appearing, or since a while probably, and we are testing them. And then we have a complete new one. It's called SOC-based, system on a chip. Actually, here you're running an entire operation system on your NIC, and basically it's a compute in a compute, or it's a server in a server, however you like to call it. And we are testing both of them actually now in our labs and achieving very promising results. The SOC-based ones come with even higher flexibility, and here additional offload becomes then possible if it's some security, firewalling, maybe voice codecs, all this can be a topic. They go beyond data plane offload, and FPGA-based comes with also very good performance. On power consumption, they are a little bit higher. That also might play a role. So, but basically at the moment it looks like between two of them they are finding their use cases, and actually at the moment we are testing them and achieving very, very good forwarding performance. If we go back to the virtual data plane use case, the data plane offload. What are the vendors? It's the typical ones: Broadcom, Intel, Marvell, Mellanox. We know them from this type of market. Then we also see some new ones which are more looking on the SOC-based implementation, like Fungible and Pensando. We're also testing those ones. So let's see what is happening here, but it looks like also the market becomes a little bit wider, or maybe whatever is happening to those companies. But at least there are some new players which are providing interesting solutions. So, and overall, with having the potential bottlenecks in mind, what I mentioned in the slide before, how we address them, data plane offload, making use of smart NICs, and selecting the right speed, the NFVI layer can actually become very, very performant. And we are now aiming to 100G connected servers and so on. And of course, you need to have the performance need on your application side here accordingly. So that's was that. Here, just as I mentioned, a very short introduction. We are used to the battle of AMD versus Intel, and based on x86 infrastructures. And we are now seeing actually that ARM processors are coming also into the game. It does not mean, in some cases it means x86 versus ARM, but we also see that those two suppliers are looking on hybrid architectures. So it looks like we are going to see more options in the server landscape, and it comes with some delay because also we need to have application readiness. Also here the hyperscalers are already making use of it, but the expectation is that we also see it in other data centers once the applications are becoming ready. So one more domain what we need to look on. That brings me basically to the end. Networking becomes even more important at the beginning to the microsegmentation and the different trends, what we see there. Multiple scaling parameters across the entire architecture needs to be considered. SmartNICs can help to increase the cloud efficiency, and probably a new battle in the data center is to be expected, however that plays out at the end. That was my summary. Brings me to the end.